So let me start. So yeah, my talk is called Reaching Planck Scale Sensitivity from Muon Lifetime Measurements in Finsler Geometry. It's a work done in collaboration with Christian Pfeiffer from the University of Tartu in Estonia. And well, but first of all, just would like to acknowledge the organizers, Gonzalo and the other organizers of this nice workshop. It has been very nice to follow the talks. So this talk now is based on this archive paper here that we wrote, Reaching the Planck Scale with Muon Lifetime Measurements. And then I'm gonna try to, from some simple and maybe some economic hypothesis here, try to derive a nice outcome that could be interesting for quantum gravity phenomenology, and that could bring some interesting perspectives of research for the next year. So if anyone is interested in collaborations. So basically, the outline, I'm just gonna drive quickly through some motivations. Then I'm gonna define what I mean by a Finsler measure or a Finsler geometry inspired by quantum gravity phenomenology. Then I'm gonna go directly to the effect, which is the time dilation that would happen in this kind of geometrical setting. And then generalize and write here some prospects and some summary. So basically, going through here, modified MDRs here means modified dispersion relations, and they provide an effective way of describing the propagation of particles in a quantum spacetime. So effectively, as the particle propagates in a quantum spacetime or propagates in a spacetime in a way that your observation is capable of observing departures from the usual equations of special or general relativity, this information can be cast phenomenologically in a way of a modified dispersion relation. And the trajectories of these particles are described by this modified dispersion relation, where here we have just some constants, alpha, beta, gamma, lambda, are just some constants for phenomenological reasons. And this modification is governed by the quantum gravity energy scale, which is supposed to be of the order of the Planck energy, which is approximately equals to 1.22 times 10 to 19 GeV. So this is an important part of, this is an important source of information in quantum gravity phenomenology. And in fact, important constraints are given by the analysis of these modified dispersion relations in the context of massless particles, by searching for a certain time delay of a race between massless particles coming from astrophysical sources. And then we have recent constraints on this kind of behavior. For instance, given the quantum gravity energy scale, given an upper bound of the order here of the so-called Planck energy. So when an upper bound, or when a certain bound is given at the order of the Planck scale, here the Planck energy, we say that we are at the Planck scale, this measurement is being performed with Planck scale sensitivity. So I'll try to, I'm showing here a different approach that we also is capable, has the potential of reaching Planck scale sensitivity, but with different kinds of particles. So let's go. So this case here, these time delays from this race between massless particles, is a time-based observable for massless particles, as I said. So the question is there a time-based observable involving massive particles? So I mean, in a way that I can have more than one messenger, more than one source of for constraining this the modified dispersion relation and quantum gravity phenomenology. So the answer is yes. Recently, the lifetime of fundamental particles has been identified as an observable that can be used to test CPT symmetry inspired by quantum gravity, however close to the Planck scale. So it's not, it doesn't hit exactly the Planck scale, but it's close to the Planck scale, and it's inspired by the so-called kappa Poincaré algebra. And then, I mean, this is a recent possibility that was raised, which basically inspired this approach that I'm showing you. I'll not do exactly what they're doing. I'm not doing, actually, not too close to what they're doing. I'm following a totally different approach, but I will reach some potential bound that is improved with respect to the one proposed here. So basically, the lifetime of particles here, it constitutes a natural definition of a clock, because it's a very well-defined phenomenon that you can, you can think that this is a clock. A clock is a phenomenon that has a well-defined duration, or it is an oscillatory phenomenon. In this case, it's a process with a very well-defined time. And then the space-time geometry, on the other hand, probed by these particles, by particles following a quantum space-time, may allow us to define a clock. We know that from special and general relativity, but I will also show here how can one define a clock in Minkowski space-time, and also can be generalized to our quantum space-time. And with this approach, this is what we use to hit exactly the so-called Planck energy. So I'm already giving a spoiler of I'm already spoiling a bit our final result. So the effective description of a continuous and commutative space-time probed by these particles has become relevant, has been a matter of research in recent years. The intuition of early approaches, now dating from 2003, says that one should expect some kind of momenta-dependent metric, which means that a particle traveling through a space-time, and if you are making measurements that can test the nature of the effective nature of quantum space-time, this particle would travel through geodesics, would obey the symmetries of some kind of momenta or energy-dependent metric. This was an intuition raised in 2003 that can be realized, in fact, that can be concretely written in terms of some very well-defined geometries. For instance, the so-called Finsler geometry, this is Finsler, where you have a metric of this tangent bundle of the space-time. So you have a metric that depends on the point and on the force velocity of a particle. So since the force velocity is related to the momentum, to the energy momentum, this is what we mean by this kind of metric. So rigorously, it is written as some Finsler geometry, and we have here some examples of papers that deal with this. And Hamilton geometry is also a possibility that deals with the metric of the cotangent bundle, where the metric depends on the space-time point and directly on the momentum, the energy and momentum, the momenta. And this has also been explored in recent years. In this talk, I'm focusing here on Finsler geometry, because Finsler geometry will provide us a natural way of defining a clock that you see in a moment. So we'll focus in this kind of geometry, the geometry of the tangent bundle. Now I'm going to show a simple algorithm to generate a Finsler function, to generate a function that describes the metric, the space-time probed by a particle obeying a modified dispersion relation. So it's very simple. It's simple analytic mechanics. So we start from an action that depends here on a parameter mu. And here we have the velocity and the conjugate momenta. Here is a Lagrange multiplier. And here is a function of the dispersion relation, the Hamiltonian of the free particle and the mass, in such a way that when this function is 0, the Hamiltonian is equal to the mass squared. So this is the modified dispersion relation, basically. Here we have a general function. So the algorithm is very simple. You vary the action with respect to the Lagrange multiplier, then you vary to, and this enforces there is the dispersion relation. You are on shell. You vary the action with respect to the momenta. Then you invert to find the momenta in terms of the points, the x dot and lambda. Then you use the momenta with this functional form in the dispersion relation to solve the equation for lambda. And then you substitute everything in the action again, and you get an action that is a functional of the position, whose extremization would give us the word lines, extremization with respect to the position. So this is the algorithm that one should follow to start from a modified dispersion relation and try to find an effective action that depends on the space-time points, and from there identify the metric. Basically, concretely, we have here a modified Hamiltonian, a perturbed Hamiltonian of this kind here, where here we have the usual quadratic dispersion relation. Here we have a perturbation parameter that could be the inverse of the Planck energy, the inverse of the square of the Planck energy, etc. I'm not fixing here any order of perturbation. And here we have a function of x and p, or in general it can be written like this in some polynomial form. So depending on the number of indices here gives the power and the momentum that modifies the dispersion relation, which in turn gives also the dimension of this parameter epsilon. So following exactly that algorithm, we find this kind of action here. It's very familiar. It's just the mass multiplied by an integral here of a function f that, for the case of a modified Hamiltonian of this form, you get the usual here metric of the space-time, but you also get a correction here. This correction depends on the mass, depends on powers here of the velocities, and also here on the norm of the velocity. And here, again, is not the space-time dimension, but it's the power of this perturbation here. So the connection with Finsler geometry, in fact, so I'm doing here analytic mechanics. So I'm trying to connect mechanics to geometry. And the connection with Finsler geometry is given by the identification of the arc length functional, S, small s here, for massive observers, which will be given by this expression. I'll just get rid of this mass. It will be given by this integral here. This function f is exactly what we call the Finsler function, and this is a Finsler measure. It's from this function that we define lengths in this kind of geometry. The Finsler metric is simply given by this expression here, the second partial derivative, the Hessian of this function squared divided by 2. Symmetries are found from this metric or from this function, since this function is the most fundamental object in this geometry. Trajectories are found by extremizing this action or the arc length. So I find the geodesics of this Finsler geometry. And this is very important because this approach is invariant under reparametrizations. So as you know, the arc length is invariant under reparametrization. You can choose any parameter that you'd like to describe a curve in a given space-time, and then the length of this curve is not dependent on the parameter that you choose to label it. So this is very important. This is a very important property. Why I'm following the Finsler geometry to describe here, to do this analysis. So that's it. Give me a functional of this form with some properties here, and then I give you a metric, I give you a space-time, and this is the space-time that particles will follow. Particles will follow here geodesics of this geometry, this Finsler space-time. So now I'm gonna go even further in the identification with the physics of I'm going back to the physics. I started from physics, then I went to geometry, then I'm going back to physics. So I'm exploring this so-called clock postulate, which is the way that I will define the clock here. which is the way that is defined clocks in special and general relativity, and I'm simply extending it to Finsler spacetime. Basically, the clock postulate says that the proper time an observer or a massive particle experiences between events A and B along a certain time-like curve, in this case a Finsler spacetime, is simply the length of this curve between these two events. This is very known in special relativity. It is the effect responsible, I mean, it's a definition, and it's indeed compatible with observations, and is responsible for explaining the so-called twin paradox, where you have observers moving which are not inertial observers, and you derive a difference in the proper time that they measure depending on their paths in space-time. But also, this postulate is responsible for explaining the so-called dilated lifetime of fundamental particles. So when a particle is in a non-inertial observer, in a non-inertial frame, you get an rated frame, let's say, you can get its lifetime being dilated. So, and this is explained here from this clock postulate, as I'm showing here from this example from special relativity. For instance, very simple here, very fundamental. We get the proper time. Consider the proper time of an undeformed dispersion relation. So you get the usual dispersion relation, for instance, this epsilon here is 0. So you get the usual Riemannian, in this case, Minkowski metric. And then, okay, it's written like this. It is parameterized by mu. So we simply transform from the mu parameter to the laboratory time, which we call the coordinate x0, which is simply label it as t. So then the proper time this particle experiences, which means that its lifetime, will be equal to this integral, and this relation here, when this velocity here is a constant. I mean, here I have the parameter mu, so I just perform the reparameterization and write this equation like this, and then I change from the parameter mu to the parameter x0, the coordinate time, or the t. And then when v is constant, we write it like this, which means that the coordinate time is simply given by gamma multiplied by delta tau. Gamma is the Lorentz factor, because it's the inverse of the square root of 1 minus v squared. And delta tau was the lifetime of this fundamental particle. So it's the proper time of the particle. And here is the time measured, the lifetime of the particle measured in the laboratory, because it's the coordinate time. And then the time obviously is dilated, because gamma is larger than 1 for relativistic particles, for particles that are not at rest. So I'm applying the same technique, but to a very known example in quantum gravity phenomenology called the Kappa Poincaré inspired modified dispersion relation. So I'm assuming a modified dispersion of this kind here, where you have a correction here with the energy and the momentum squared. And then I'm identifying, obviously, the function h that perturbs the dispersion relation. And the epsilon is given by the inverse of this kappa. This is epsilon. So I'm using this example that is extensively studied in the literature, and I'm just wondering, okay, let's suppose that a particle obeys this kind of dispersion relation inspired by this well-known proposal. What do we find for this dilated lifetime? What kind of constraint can we place on this dilated lifetime? This is the Finsler function that can be derived from this modified dispersion relation. So it's basically the usual Minkowski measure plus this correction here. And then we derive the dilated lifetime of this form. I just used the same technique of the previous slide. So it is given by the usual gamma delta tau term of special relativity, typical of special relativity, plus here a correction that goes with gamma. Gamma to the cube is the dominant power here, and the mass, and then the kappa, which is an energy, this kappa parameter. However, in order to properly compare this expression with data, we need to transform from the velocity Lorentz factor, gamma, which is given by this quantity. Actually, this is gamma, the square root of, this is gamma squared. And we transform it to the momentum Lorentz factor, which is given by this quantity here, which is the energy divided by the mass. So this can be done easily. You just have the energy here, the definition of the energy, the conjugate energy in the from the Finsler function. Then you find this kind of expression, then you invert, and you find that the velocity Lorentz factor is given by this correction here, gamma bar, where gamma bar is P0 divided by m, and then you have this correction that depends on the kappa parameter. So substituting back into the previous expression, we find that the dilated lifetime of a particle is given by the expression that one would find using special relativity, and this dilated by this factor here, the energy of the particle divided by its mass. And the correction is given by this factor of, actually developing a bit, it is given by this factor here for high energetic particles. It is given by this quantity here. So you see that it grows with the third power of the energy. For small masses, it also amplifies the effect. And then this dimensionless quantity, is what governs this kind of correction. So let's see what happens if we compare this expression with the uncertainty in the measurement of fundamental particles that are tabled in the literature. Concretely, we are going to compare that factor delta of our time dilation formula with the relative uncertainty, that actual measurements of the muon lifetime. We'll focus here on the muon lifetime. So we are simply investigating the consequences of assuming that particle accelerators, for instance, like the LHC or the planned FCC, could measure this dilated lifetime with similar precision. So the lifetime of the muon has been measured at low energies with this accuracy here. So it is, you have an uncertainty of the order given by this sigma, and then we just explore what is the consequence of assuming that facilities could perform, like accelerators could perform this kind of measurement with similar uncertainty. So to do this, I just need to compare the relative uncertainty, this quantity divided by the lifetime, the measured lifetime, which is given by 10 to minus 6. It's an 8-dimensional quantity. So I just need to compare the relative uncertainty with the delta that corrected the dilated lifetime. So assuming the energy scale at the LHC and supposing that the measurement can be done with the same relative uncertainty, so it's a very let's say it's a very optimistic hypothesis here. I get a very optimistic input. I get, let's see, I get a bound on the kappa parameter given exactly by 1.2 times 10 to 19 GeV, which is nothing but the Planck energy. So with this approach, using present uncertainties, we hit the Planck energy, we hit the Planck scale, we hit the Planck energy exactly in the eye. So this is a very optimistic result, especially due to this relative uncertainty, because it's the measurements are done in a very controlled way. And then one should see how this could be done in accelerators, but still it has a nice potential for the future. And in fact, the planned future circular collider, the planned FCC, shall reach an energy of the order 50 TeV, which would increase here in 1 order of magnitude the Lorentz factor, which gives 3 orders of magnitude higher, makes our effect 3 orders of magnitude higher, more intense, which can allow to have a less precise measurement of the muon lifetime. So you can alleviate the need for precision with energy, because our amplifying factor is given by a third power of the Lorentz factor. So just to finalize, we also derived the same kind of effect for general modified dispersion relations of the isotropic kind, which means that they do not depend on a certain direction in space. They depend on the modulus of the moduli of the momentum, the spatial momentum. So it's the skew here. So you have powers, and it is given by a polynomial of this form. So we get this kind of expression that can be compared with many approaches, many existing and future approaches in the literature. You just need to transform from for each case from the velocity Lorentz factor to the momentum Lorentz factor to find exactly the quantity to be compared with data. So just we have some examples, as this is just for completeness, some known examples in the literature and how we can reproduce all of them in this table. So just to summarize, so we derived a general Finsler measure, which would be the natural geometry followed by particles that are sensitive enough to modify dispersion relations. We simply extended the clock postulate to this Finsler geometry to find corrections in the time dilation of fundamental particles. And we found, so the outcome is very positive. We found that using the energy scale of present or near future particle accelerators, we reach the Planck scale, if we assume, obviously, that those measurements can be done with similar relative uncertainty as the measurement done for low energy muons. And we also derived a time dilation formula that talks to the whole community from this general isotropic modified dispersion relation. So some prospects here are, what are the concrete prospects for measuring this dilated lifetime? What about other geometries? What about Hamilton geometry and related formalisms? What about other particles? For instance, what kind of bound I can get from them? And what about other kind of observations? What about observations coming from cosmic rays? Can I reach second order in Planck scale? So this is all to be done. This is my email. So I think I managed to answer these questions that Gonzalo proposed for us. That what is the effect? What am I proposing? I'm proposing that we can measure, we can have a corrected lifetime in these natural effective geometries probed by particles traveling in a quantum space-time. Why this is important? It's important because of the result that we reach Planck scale, and also because the hypotheses are, I think they are very economic. I mean, if you assume modified dispersion relations and the idea of an effective space-time traveled by them. And then what to do next? I think these are some of the main, this is not an exhaustive list, but these are some prospects that can be followed in the next months. So thank you for your attention.
Okay. Thank you. So can you hear us and see us?
Yes.
Okay.
Okay. Yes, I can see you. I just have this. Yes, I can.
The microphone,
yes.
Our microphone, okay, because we are testing this new system. Okay, so Iarley, nice to see you and to hear your recent work. So it's been very, very interesting. So it is now time to ask him questions. I think that Adria had some questions or comments.
So I wanted to ask you whether you know if there is any formulation of fields, like field theory on Finsler space-time. Like for example, do you know how a scalar field behaves or couples to the Finsler metric and stuff like that? Can you derive, for example, in the econal limit, whether scalar particles described by a scalar field follow geodesics and so on? This kind of
Yes.
do you know if it's done already or maybe?
I know that there are some things done in this direction involving the so-called renders renders geometry, which is a particular case of Finsler geometry. So in this case, the authors constructed an action for a scalar particle, however, with a, let's say, with a kinetic term governed by the Finsler metric. So you have powers in the for the kinetic terms other than squared powers, and then they do exactly this. They derive the iconal. They follow the iconal approximation, and then they derive that the momentum, the modes of this field follow the geodesic equation of the Finsler spacetime. In this case of renders geometry, which is a particular case. And this is also something that could be done here in this case. I mean, starting from the Finsler geometry, from the Finsler metric, and trying to construct a field theory, let's say, and trying to check, I don't know, the decay of particles, things like this.
And so, do you know, for example, these kinetic terms, they also, because the metric depends on the velocities in general.
Yes.
So, would there be, could this formulation be similar to a non-minimally coupled formulation of a field in a Riemannian space or something like that, or maybe it looks otherwise?
Well, let's say usually there's no minimal couplings in Riemannian. I mean, the matter is coupled to the curvature, right? So to derivatives of the metric in this case. I mean, well, the usual coupling that the usual coupling that people do to derive this kind of let's say this kind of action for field theory is the minimal coupling, however, with the Finsler metric. I don't know. I think this has not been investigated if this information of the Finsler geometry and of this let's say perturbed behavior of matter in the Finsler spacetime can be absorbed in a non-minimal coupling of a Riemannian spacetime. As far as I know, this has not been investigated yet.
Okay, so one last thing. So the trouble that I find with these ideas is that given that the Finsler geometry depends on the velocity of the particle, let's say, it doesn't look like a universal geometry, like a background geometry where matter can move. Because if any particle, depending on its velocity, will see a different metric, then
but
somehow universality is lost, right?
Well, but I mean, the main issue about this is the matter of localization and how can so these particles they follow this Finsler geometry, they probe this Finsler geometry, but you as a massive observer, you do not. The idea is that, okay, I obey the usual modified dispersion as well known, so in principle I do not, so I describe space-time usually from a Riemannian, let's say, space-time, or at least a non-Finslerian space-time, so probably with no metricity or torsion, but not of the Finsler kind. However, the particles, they are sensitive to this geometry. And how can this, let's say, effective quantum geometry be manifest in the physics of this particle? I'm saying that it could be manifest in the decay time of these particles. So or at least in the way we measure the decay time of these particles due to the propagation of these particles in this quantum space-time. So that's kind of the idea that I'm trying to, let's say, to defend here. So it's just a Finsler geometry. I mean, it's a Finsler geometry. It's a very concrete geometry. It's a centenary geometry. It has been, I mean, we have, it's a very robust, you know, theoretical, I mean, geometrical, mathematical construction. And then this is just the link to these, to observe this effective interaction of a particles with this effective quantum spacetime, let's say. And it's manifesting in the lifetime of the particle and the way we measure it due to its propagation in the spacetime.
So, yeah, any other question?
I have a suggestion actually. So, do you think, because you know, sometimes you can model particles propagating in a non-trivial background of some field, as if they were propagating in a curved space or in a manifold. Have you tried to, or do you know if there are any, for example, I was thinking that a charged particle in a magnetic field could sense somehow a Finsler geometry, because the way it sees the magnetic field or the magnetic field affects the particle depends on the velocity. So it might be modeled in an effective way as a Finsler, as a particle propagating in a Finsler background. I don't know if there is any results on this direction. Just as a suggestion.
Well, yes, I mean, in the action of a particle coupled to for potential. For instance, here we have the action of a free particle. Okay, so let's suppose here we have the usual Riemannian case. This is not no without corrections with this epsilon given equals to 0. So you have a usual Riemannian action. And then you have here also its interaction with an electromagnetic field. So you have here the connection with the A mu x dot mu. And then it's a known result that if you try to imagine this, what would be some kind of Finsler? Let's suppose that this action, this full action with this interaction term, is in fact a Finsler measure. So what is the Finsler? Is there a Finsler geometry behind this in this approach? And the answer is yes. This is a known result from many years ago, but so yes, I mean, but I think in this case it's similar. It seems it almost touches some kind of interpretational issue, because I mean, just writing the action and then you are trying to find an effective geometry that describes the free particle plus the interaction. And it touched the spirit of this approach. It's like, you know, the particle is interacting with a quantum spacetime, so you have a non-trivial term here, and this is giving me a non-trivial Finsler metric, and it's giving me non-trivial results in its lifetime. Am I clear?
Yes, yes. I mean, it makes sense that it's known. So.
Okay, then. So, any other question from the audience? There are no comments in the chat. So, if not, then let's thank Iarley again for his nice talk. And thanks for joining us again. It's been nice to have you here.